Welcome, everybody. So now we are honored to have Professor Bar-Natan from University of Toronto going to tell us about knot invariants from finite dimensional integration. Professor Bar-Natan is the world's leading expert on knot theory, and let's welcome him.
I don't know if this description was accurate, but anyway, thank you. Also, a few minutes before the beginning of the talk, Shin looked at the formulas on the handout and said they look awful. So, good. You can hate them as much as you want. Hate them as much as you want. They still represent the strongest knot invariant, genuinely computable knot invariant we currently have. Likewise, you can hate my talk as much as you want, you can hate me as much as you want, but I'm still going to tell you about the strongest, genuinely computable knot invariant we presently have, so you cannot ignore it. This said, hopefully you read my abstract. I'm going to tell you about how to write a Lagrangian that is sort of defined on the knot. So its domain of definition is some discrete space, unlike the continuous spaces of quantum mechanics or quantum field theory. And when you integrate this Lagrangian, you get knot invariants. These Lagrangians, you get knot invariants. Ivan, take a handout from the chair over there. And those knot invariants, I claim, are excellent. And I should have said that this work is joint with Roland van der Veen from the University of Groningen. Hopefully you're all holding a copy of the handout. If not, a few more copies are still on the chair by the entrance. I should thank you for inviting me to Beijing and tell you that omega epsilon beta is defined to be http://icds24, and materials related to this talk are at that URL. I should acknowledge my sponsors, the NSERC and the Chu Family Foundation, New York City. And I should start. So first of all, what are knots? So knots, well, okay, there are three-dimensional circles, circles embedded in R3 modulo a certain equivalence relation. Alternatively, they are pictures in the plane that look roughly like that. I should have said oriented, so this line carries an orientation, but I failed to indicate it. Modulo a certain moves called the Reidemeister moves. So Reidemeister 1 says that if you have a kink, you can undo it. Reidemeister 2 says that if you have two strands slightly overlapping, you can remove the overlap. And Reidemeister 3 is this lovely picture. I will not attempt to describe it in words. But if you impose these three relations on the set of knot diagrams, you get knots. Okay? Now, knot theory is much more than telling knots apart. There are many other questions to ask, but let's start with telling knots apart. It's actually very hard to decide whether or not this knot is equal to the trivial knot, the circle with no crossings. Because possibly you will have to do these moves for a very long time in order to get from this knot to the trivial circle. And how would you know? I mean, if the number of moves you have to do is quadrillion, how would you know if this is equivalent to the empty circle or not, to the trivial circle or not? So the answer is that you seek knot invariants. So knot invariants are functions defined on the space of diagrams that do not change when you make these moves, so they descend to the quotient by the move, so they descend to knots, and which take values in something simple, so numbers, polynomials, matrices, something like that, where it's easy to tell if two things are equal or not. And then you compute a knot invariant on this knot, and if it comes out 17, and on the empty circle it comes out 16, you know they're different. Okay? Now, what's good about knot theory? It's at the center of low-dimensional topology. Lots of other things in low-dimensional topology, 3 manifolds, 4 manifolds, can be described in terms of knots. And the theory of knot invariants, so there are constructions of knot invariants coming from pretty much all of algebra. So if you want a motivation to learn all of algebra, just go in sequence and learn all the knot invariants there are. Okay? What's the agony of knot theory? It's that points 1 and 2 don't talk to each other very well. So first of all, there are many invariants, but there aren't enough topological applications of them. And the fancy algebra that you end up using for different invariants isn't coming naturally from knot theory. It tends to come from all sorts of different directions, but if you were a topologist, you wouldn't discover this algebra on your own, almost never. So the moral, at least for me, is that we are still missing something very foundational, very basic about the relationship between knots and algebra. There ought to be a better understanding, which we still don't have, and my talk today is not going to help you. I'm just highlighting the fact that there is still a lot missing. In fact, what I'm going to tell you is yet another fancy algebra that leads to fancy invariants, maybe the fanciest. And I really wish one day we will understand it. So again, you can hate me for not giving you answers, but now you should be thinking about it from the practical, selfish perspective. The fact that I can't give you answers and I'm old means that the young people here will give the answers one day, so you should be happy. Okay, sorry for being so silly. Anyway, let's start with the example. So let t be some variable, just a name of a variable, and let epsilon be a variable which squares to 0. So epsilon squared is equal to 0. I'm looking at things modulo epsilon squared. Given a knot, I'm going to tell you how to construct an integral. And again, you can hate it as much as you want. It doesn't matter. It's still it's the second best knot invariant that's genuinely computable. So so here's what you do. First of all, you draw the knot in the plane as an open knot. So you cut it open at some point. It doesn't matter where. And you draw it in such a way that at all crossings, the crossing points, the edges, are facing up. So all the edges are facing up. And then you label the edges, you number the edges. So this is edge number 1, 2, 3, 4. Oh, and I forgot to say, sometimes an edge rotates because the edges all begin pointing up and end pointing up. So sometimes it has a rotation number. If it has a rotation number, you mark it. So edge number 4 rotates -1 times because this is a rotation clockwise and I count rotations counterclockwise. So I call phi 4, the rotation number 4, I say it's -1. And when an edge rotates, I make an extra cut on it. So the next edge is this tiny segment here and it's number 5. 6, 7, 8. To each edge, I associate a two-dimensional space with two variables on it. labeling it. So this is R2 and the variables are P1 and X1. R2 and the variables are P2 and X2, and so on. And then eventually, I will integrate over the product of all of these spaces, excluding the last one. So it's R to the 14, where the variables are P1, Pi, and Xi. And I should say that to eliminate constants like pi, I take the measure on the real numbers to be 2 pi to the minus 1/2 times the standard Lebesgue measure on the reals. That's my measure. Okay? And then I associate an expression for each feature of the knot. The features of the knot, in this case, are the crossings, so there are 3 expressions corresponding to the 3 crossings, and the rotation, so there is a 4th expression corresponding to the turning of only one of the edges, and then I integrate the product of these 4 expressions. The expressions are of the form a constant times the exponential of the Lagrangian. If you have a crossing of sine s, if you don't know how to figure out the signs in knot theory, it doesn't really matter. There is some right-hand rule like in physics, but it doesn't matter. Crossings have a sign, okay? So if you have a crossing of sine s, in which the upper strand is I and the lower strand is j. So for example, here the upper strand is 3 and the lower strand is 7. So this is the crossing x37 plus because it's positive. The expression I associate with it is t to the power s over 2, this is the constant, times the exponential of x to the times the exponential of the Lagrangian of that crossing. And likewise, for a rotation, I associate t to the phi over 2 times the exponential of the Lagrangian of that rotation, where the Lagrangian of the crossing is this awful expression. Hate it as much as you want, I don't care. Okay? So what is this awful expression? It depends on the variables only near the crossing. So basically, well, if the crossing is between 3 and 7, the variables near it are 3, 7, 4, and 8. So it depends only on I, j, I plus 1, and j plus 1, and it's given as a quadratic. This is the first 2 lines. Plus epsilon. Epsilon, I think of it as a small thing because epsilon squared is equal to 0, so it's like a perturbation. So epsilon times something which is quartic. And again, hate it as much as you want, it doesn't matter. Here is this quartic thing, if you can see it because you're far. Okay? So for the trefoil, z, the integral, is t, this is the product of all the t factors, times the integral of the exponential of the Lagrangian of the trefoil, relative to 14 variables, where the Lagrangian of the trefoil is the sum of the Lagrangians of the components, right? Because it's the product of exponentials, so that's the exponential of the sum. And it turns out to be sum as I goes from 1 to 7 of xi times pi plus 1 minus pi, plus t minus 1 times a certain contribution from the red crossing. Well, for your convenience, I've labeled the crossings in colors, so red, green, and blue. So a contribution from the red crossing, green crossing, and blue crossing, plus epsilon over 2 times a perturbation, again, one term of the perturbation coming from each of the crossings, plus another term for the perturbation coming from the rotation number in purple here. Okay?
Excuse me, why is the number, why is the dimension 14? Why P1, P7, X1, X7? What do you actually count?
I'm counting the edges of the diagram. So the edges are 1, 2, 3, 4. edges 4 has a rotation, so I cut it. Sorry, these are the rules. I'm setting the rules. So edge number 4 gets cut, and then here there is little edge number 5, 6, 7, and there is edge number 8, but I do not integrate over it. So in general, for a knot, if you have a 50 crossing knot, you're going to have 2 times 50 edges, roughly, and then some of them are going to be cut if there are rotations when you draw the knot. Okay, so it's going to be 100 and some integration variables for a 50 crossing knot. Okay?
Why does the integral converge?
Sorry?
Why does the integral converge?
I don't know. I'll answer later.
So are you left with P8 variable that you haven't integrated out?
Yeah, so the last variables, the end result turns out to be independent of the last variables. Okay? So in the case of the trefoil, you can compute this integral. I'll show you later how. And the result is z is equal to t minus 1 plus t inverse times the exponential of epsilon times something crazy. And you can rewrite it as delta inverse times the exponential times some fixed polynomial times rho 1 divided by delta squared. And here delta turns out to be the Alexander polynomial, and rho 1 is the so-called Rosansky-Overbay polynomial. You can check about it in references over there, and references over here. And delta, the pair delta and rho 1 taken together are the strongest knot invariant we know. Sorry, second strongest knot invariant we know. I'll tell you later. Okay? But before I'll tell you more, I want you to just look at this integral a little bit, and if you have physics eyes, then it looks less horrible than just a horrible formula. So basically, the first term here looks like the kinetic energy in discrete quantum mechanics in phase space. So this is like xp dot. Okay? Then there is a second kinetic energy which is multiplied by t minus 1. So t is usually thought of as being close to 1. So t minus 1 is a small parameter. So again, a small parameter times a fix, a correction to the kinetic energy. And then there is some interaction term, which is horrible, I admit.
Well, you were saying it is nothing like Wheaton's, but maybe it is something like first term of something infinite dimensional when you have just first term of something horrible but more powerful.
Maybe, part of the reason for giving this talk is to annoy you so that you will explain it better than me.
Px dot is not a kinetic energy.
Sorry?
Px dot is not a kinetic energy. It's indeed like a finite dimensional version of Chern silence, if you wish. Kinetic energy is p squared over 2.
I said in phase space. There is a description of quantum mechanics in which you write qp dot instead of p squared.
With zero Hamiltonian, it's not a kinetic energy.
Sorry?
You also have a Hamiltonian to be added to xp dot.
So, okay, if I annoyed you, good. Anyway, so theorem, yes?
But still, not to make it personal in any way here, but still a priori we know it is topological invariant, right? This we know, right?
No, you don't. A priori? How do you know that?
Because of the beginning of your talk, which I missed probably.
No, sorry. No, you don't know that it's a topological invariant. If you change any of the little constants there, it dies.
It appeared to be a posteriori, it appeared to be a topological invariant in terms of Alexander and Rosansky.
Yeah, but how would you know that?
But do you make a point this procedure produce topological invariance?
Yes. In fact, this is the theorem, or first theorem.
Yes.
So theorem, Z is a not invariant.
Exactly what I'm asking.
And
It is a priori clear, right?
it's not a priori clear. It's totally not a priori clear. It requires a proof.
Requires a proof, yes, of course.
Okay? And the proof is basically you have to show invariance under the Reidemeister moves. It's not quite the same Reidemeister moves as before because I was insisting that the edges will be pointing up at the crossings. So there is a little bit moves, there are a few further moves that have to do with turning the edges, with interaction between rotations and crossings. Swirling a crossing is the same as not swirling the crossing, but roughly it's just the Reidemeister moves. And the proof is, so basically, since the definition of the integrand was local, if you want to prove that, say, the integral corresponding to the left-hand side and corresponding to the right-hand side of the Reidemeister move are equal, well, all you have to do is to integrate over the internal variables to the move first, and then the integral with respect to the internal variables to the move on the left is equal to the integral on the right, and then by Fubini you can continue and integrate the rest of the variables later on.
What sort of solutions to the Young-Baxter do you get from that?
I don't get the solution to the Young-Baxter. I don't know what the Young-Baxter equation is.
Do you know? Do you have invariants of braids in any form?
Of course, you restrict your attention to braids, you get invariant of braids. You have to work a little bit, but it's not a Reshetichin-Turaev style invariant. So if you're looking for Young-Baxter equations like products of operators R1, 2, R1, 3 something, it's not here.
There was already a question about conversions of the integrals.
I'll tell you in a moment.
But I mean, it's related because if they are not convergent, as you doubt, you cannot easily use this logic.
Indeed. You're right. Okay. But now I have to tell you how do I compute these integrals. And that partially will answer your question. Okay? So I have these integrals, right? I'm telling you, use Fubini, compute this, compute that, but how do you compute such integrals? So all of these integrals are perturbed Gaussian integrals. So let me spend a minute telling you, some of you, the physicists here definitely know it very well, but nevertheless, let me spend a minute telling you how to compute perturbed Gaussian integrals. So perturbed Gaussian integrals are integrals over a finite dimensional space of relative to some variables xi, x1 up to xn, which I'll summarize as dx. My measure remains divided by square root of 2 pi. And then I want to integrate the exponential of something quadratic in the variables. Here the variables are xi and xj. Before they were xi and pj. Sorry, xi, xj, pi, pj, many more variables. Plus a perturbation, and I'll be thinking that the perturbation is a polynomial in x, and that in some sense it is small relative to the quadratic. So for example, it could be multiplied by epsilon, where epsilon is a power series parameter, and I even assume that epsilon squared is equal to 0. Okay? So how do I compute such an integral? Well, there is a standard ways in physics textbooks. I'm going to use a slightly different route. So hence it's alternative Gaussian integral. First of all, I'm going to set z sub lambda. I'm introducing a new parameter lambda, and I'm setting z lambda of x. So it's a function of a variable x, and z lambda of x is basically the same integral, except I divide the quadratic form by lambda, I change the variable of integration to y, So instead of integral dx, it's called dy. But x re-entered the picture because I insert it into the perturbation. So I look at the perturbation at x plus y. Now, if you look at z1 of 0, so if you set lambda to 1, then end x to 0, then x drops out, lambda drops out, and you get back the integral you started from. If you look at the limit where lambda goes to 0, so if the lambda goes to 0, the coefficient in front of the quadratic goes to infinity, so the Gaussian becomes more and more like a delta function. I'm making a lot of analytic assumptions and they all turn out to be completely irrelevant later, so bear with me. Okay, so I take the limit as lambda goes to 0, this term becomes a delta function, and therefore z0 of x is just replace this part by a delta function at y equals to 0, and you get essentially the exponential of v of x. And finally, you look for a differential equation for z lambda as a function of lambda. So you differentiate with respect to lambda. Now, I will not go through the derivation of the differential equation because it will bore you and because I don't have enough time. I'll only tell you that the differential equation you get is, well, again, here is the derivation, and the differential equation you get is that the derivative with respect to lambda of z lambda is 1/2 times gij, the derivative of x with respect to xi times of the derivative with respect to xj of z lambda of x, where this is multiplied by coefficient, so it's roughly a Laplacian, but it's multiplied by a coefficient, and the coefficient is the inverse matrix, is gij, or the green function, as I call it, and it's the inverse matrix of the quadratic A, okay? And so, when you solve this PDE, it's roughly a hit equation, and the solution is that z lambda of x is equal to the exponential of the Laplacian applied to the initial condition, which is the exponential of the perturbation, and that's the solution. Now, again, if you are familiar with physics, this is where Feynman diagrams are born. So basically, v of x is a polynomial in x. So this computes z lambda of x. Now to compute the integral, you set lambda equals to 1 and x is equal to 0 at the end. So this is where Feynman diagrams are born, because you see this is like a polynomial in x. You differentiate it, each derivative has to hit one of the x's that appears in v, and the combinatorics of how this happens is summarized by Feynman diagrams. So this is really the theory of Feynman diagrams. And the next things that I do is I switch from general Feynman diagram to so-called connected Feynman diagrams. And this just means that I set z lambda, this was calligraphic z lambda, this is just uppercase z lambda, to be log of calligraphic z lambda. And then by a simple substitution, you substitute it into this equation, and you get that z0 is v, and the derivative with respect to lambda of z lambda is some nonlinear operation, or nonlinear operator f applied to z lambda, so it's f of z lambda, and the nonlinear operator is written here. It's a Laplacian plus another term. Again, all of these are routine verifications. So anyway, how do you solve this equation, which I like to call the synthesis equation because it synthesizes Feynman diagrams, if you interpret it. So you solve it by Picard iteration. Basically, we have an ODE in an infinite dimensional space. The derivative of lambda of z lambda is some operator applied to z lambda. And Picard tells you that in order to solve such equation, so if you have an equation of the form d lambda of f lambda is equal to f of f, then you start with the initial condition and you iterate. F goes to f0 plus the integral from 0 to lambda of f, and you seek a fixed point for this iterative procedure. In our cases, and I'm not right now explaining why, but it's not terribly difficult, the Picard iteration always ends after finitely many iterations. And this means that all the analysis is completely irrelevant because derivatives make sense for polynomials, and all you have to do is iterate differentiation and integration. Integration also makes sense for polynomials. So all you have to do is to iterate differentiation and integration finitely many times, and then you get your answer, and so the answer is completely algebraic. It is an algebraic function in the inputs, okay, in the coefficients of A and of V, of the quadratic form and of V. So let's define the Gaussian integral, or the formal Gaussian integral, to be the result of this process in ignoring convergence. And now you have to ask, does Fubini still hold? So I could give an independent proof of Fubini in this language. I could also cheat a little bit, so I'll say, I don't know, I'll cheat a little bit. So basically, all of this is correct in a Zariski dense set of parameters. So for some parameters, basically if the quadratic is imaginary, then the integrals are oscillatory, and then everything here is correct in analysis. And since Fubini holds in a Zariski dense set of parameters, and since the answer is algebraic in the parameters, Fubini holds for all parameters.
Can you repeat why you have only finitely many terms?
No, I cannot. I did not explain why there are only finitely many terms. I said, in our cases, there are only finitely many terms, in the cases that I will consider.
Can you explain why?
You have to go through these cases one by one and explain and understand each one.
Generally, of course, it's a series of numbers.
Right. But in a surprising number of cases, it's actually finite. In fact, I'm going to give you a few examples. Okay? So, you know, I think I'm living up to what I said at the beginning. I'm making you hate me. And that's fine, again, because the results speak for themselves. So here is an implementation. Hate me some more. I love to implement. I love to write computer programs. Mathematicians hate it. I love it. So here is an implementation in Mathematica. If you want to see the Mathematica notebook, it's available at omega-epsilon-beta/AP. So first I load some standard knot theory packages that have nothing to do with, that just have to do with naming and enumeration of knots, not with the actual computations. Then I define the canonical form of an expression. It's not interesting, it's just how I want to print my polynomials. And now comes the core. The core is how do you integrate. So first I let E, blackboard E, behave like an exponential. So E of A times E of B is E of A plus B. I'm telling Mathematica that I want to use this rule. Then there is a hack. so I'll tell you about it later. And then there is the main integration program. First thing I do is I unprotect the word integrate, because Mathematica has a meaning for it already and I want to overwrite it. Okay, and at the end I protect it, because if you, I protect it back again, because if you raise the toilet seat at the end you have to lower it. And then I define the integral. So the core of the definition is in yellow, and it's precisely the formulas I told you. So if you want to integrate a constant times the exponential of a Lagrangian, d, a list of variables, first thing you do is you find what is the quadratic, and you do it by taking the second order derivatives of the Lagrangian and substituting all the variables to 0, so that gives you the quadratic. Then, if the determinant of the quadratic, which you call delta, is equal to 0, then you cannot invert the matrix, the correlated, what is it called, the matrix of the Gaussian. So
do you call it Lagrangian because something looks like kinetic energy?
Because it looks like physics, because I want to suggest the look like physics. Anyway, if you cannot invert the kinetic energy, you return, Q is degenerate, and you return it in red to I don't know. And otherwise, you find a fixed point of the process as follows. So you let dz be the list of derivatives of z, ddz to be the list of derivatives of dz. So this is the matrix of second derivatives. You let fz be the sum of g alpha beta times the second derivative plus this correction term. And finally you look for the fixed point of z goes to z0 plus the integral of fz. So this is precisely what I said before. This is precisely an implementation of Picard's iteration for the synthesis equation. And the hack, so the hack is in pink, the hack is that if I know that something is going to integrate to 0, I project it. So I add a projection which allows me to kill terms that I know will never be visible. So for example, well, the initial definition of the projection is the identity, so you don't do anything. But later, I will want to integrate up to epsilon squared, and then the projection will kill anything in which epsilon appears to a power higher than 2. Okay, so this is the minor hack. And at the end, I output z where lambda is substituted, where I set lambda to 1 and set all the variables to 0. Okay. So let's run a few examples. So this is me. I'm asking the computer to compute the integral of a Gaussian. In fact, it's the Fourier transform of a Gaussian because I'm adding e to the I psi x dx. Yes?
When you say fixed point, it's fixed point in which space?
Space of polynomials in all of the relevant variables.
So in the space of, when you say polynomials, in the space of coefficients of these polynomials.
I suppose, yeah. Okay? So the computer, here's the computer, it outputs that this is e to the minus psi squared over 2 mu divided by the square root of mu. And if you've seen Gaussian integration, this is the result of Gaussian integration. Here's a slightly more sophisticated example of the same thing. I define Fourier of Gaussian to be the integral of a shifted Gaussian. And again, I integrate it, and the computer outputs that this is the result of the Gaussian integral of, the Fourier transform of a shifted Gaussian. Then I ask the computer to compute the inverse Fourier transform by taking the Fourier of a Gaussian and multiplying it by the exponential of minus I psi x. So if you look at it, this was a Gaussian in psi, It's quadratic, it's the exponential of a quadratic in xi. So this is again the integral of a quadratic, and the computer outputs the same thing that I began with. And this is nearly a proof of the Fourier inversion formula. It's a proof of the Fourier inversion formula for shifted Gaussians, but shifted Gaussian is essentially span the space of functions. So this more or less proves the Fourier inversion formula. Here's another example. Now I let the Lagrangian to be a quadratic in two variables plus something linear just to add some spice. And then I'm telling the computers that I want z12 to be the integral of this thing, d, the two variable, dx1 and x2. The computer outputs this. And then I tell the computer, let z1 be the integral with respect to x1, and let's check if z12 is equal to the integral of z1 with respect to x2. This is precisely Fubini. Computer outputs the same result and says that the integral with respect to the first variable, and then outputs true to say that these two things are equal. So we verified Fubini in one particular case. This is more or less just testing of my program. And then, yes?
In this case, your integrals are obviously convergent, or you don't...
I don't care if they're convergent. No, they're not obviously convergent.
Just you don't put the conditional parameters.
I didn't put any condition on the parameters. I don't care if I don't know what's convergent. I don't know any analysis. I never knew any analysis. Why would I know analysis? Okay, sorry, I'm just being silly. Anyway, now I let the projection to be add to the input O of epsilon cube to the 13, which effectively means that you drop epsilon to the 13 or higher, so you're only computing up to epsilon to the 12. And I'm letting the integral be the integral of, essentially this is 5 cube theory, one-dimensional 5 cube theory. And, I hit enter, the computer outputs that this is the answer as a power series in epsilon up to epsilon squared. And I look at this sequence of numbers, and I have no idea what they are, so I type them into Google, and Google finds them in the online encyclopedia of integer sequences. So basically the sequence of numerators, 5, 5, 1, 1, 0, 5, 5, 6, 5 is here, 1, 5, 5, 1, 1, 0, 5, 5, 6, 5, and so on. And then the online encyclopedia of integer sequences says that these are the numerators of the mass formula for connected vacuum graphs on 2n nodes for a phi-cubed field theory. So I feel vindicated, my program is working. Now that I know that my program is working, I want to run it in the cases that I care about. So I let K be the mirror of node 3.1 because the node I drew before is the mirror of the standard 3.1 node. And I let the computer print the feature of K. The features of K are, well, first of all, they are along an interval of length 7, and second, I have a rotation -1 on edge 4, a crossing 1, 5 with sign 1, a crossing with the upper strand 3 and the lower strand 7 with sign 1, and so on. Then I define the Lagrangian. So the Lagrangian of xij with sign s, hopefully this is the same formula that appeared before. If it isn't, this is the authority, not the tech thing, right? Because this one was really tested. And then I tell the computers that the variables for k are just a table of pi and xi running up to the right index. And just for testing, the variables for our k, the trefoil, and the Lagrangian for our k, the trefoil. So the variables are p1 up to x7, and the full Lagrangian is the sum of the pieces for the crossings and the rotation, and it's this horrible expression. And then I tell the computer dropping terms bigger than setting epsilon squared to 0, let's compute the integral of the Lagrangian time d the variables, and the computer outputs the answers that I promised. So there is a faster program to compute row 1. This isn't very fast, it's actually quite slow, and there are more stories about it at a certain reference, but before telling you the stories, let me tell you that this is strong. So this invariant that we just constructed, so it's really a pair, delta and rho 1, the Alexander polynomial, which is like appears in the formulas in the denominator, and rho 1, which appears in the exponential multiplying epsilon. So this pair attains 53,684 distinct values on the nodes with up to 14 crossings, which means that it misses 6,253.
Is there any evidence that your invariant dominates, say, Jones or Humphrey, that you can get?
It doesn't dominate Jones or Humphrey. It is just stronger than them. Mainly, it separates more, but without dominating. If you look at the pair of Hovanov homology and the Humphrey polynomials, they attain fewer values, so the deficit is greater. The pair Alexander and theta, which I will discuss later, has an even smaller deficit, 1,118. So it's almost 10 times better than Humphrey and Hovanov taken together. Furthermore, all of these invariants that I'm discussing today, delta, rho 1, and theta, which I will discuss later, are computable in polynomial time, and hence even for very, very large nodes. And so, even if the formulas are ugly, and the formulas for theta, which I will discuss later, are even uglier, these are the best invariants we have. At least best genuinely computable invariants we have. Anyway, why are they polynomial time? Basically because we're going to integrate the exponential of that. Here we have epsilon multiplying a sum of terms, one term for each crossing. Let's ignore the rotation number, for each feature, okay? And the exponential of 1 plus a sum of something plus epsilon, basically you can ignore, you expand the exponential in power series and you can ignore the second powers because epsilon squared is equal to 0. So basically the end result ends up being a summation over the features of the node, and for each feature it's a single integral of a polynomial against a quadratic, against the exponential of a quadratic. To do this you have to invert the quadratic. Inverting the quadratic is inverting a matrix. Inverting a matrix whose size is roughly the size of the node is efficient. So basically, to compute this invariant, all you have to do is to invert a matrix whose size is linear in the size of the node, and then sum over the features something that is computable in constant time. So it's a very easy computation. I have to prove invariance under Reidemeister 3, and I'm running out of time. I only have 10 minutes to go. So I'll do it very, very quickly. Basically, my programs are good enough not only to compute, but also to prove invariance. but you have to be a little bit careful. So you want to prove that the integral for the left-hand side of the Reidemeister move is equal to the integral for the right-hand side of the Reidemeister moves. You're going to have variables xi, pi, xj, pj, xk, pk, and then xj plus 1, pj plus 1, and so on, and xk plus 2, and so on. And the middle variables, the one with a plus 1, not plus 2, and not plus 0, so the middle variables will not touch anything else. In principle, the variables with k plus 2 could also get contributions from the crossing above. And the variables with xi or pi, with I or j or k, could get a contribution from the contribution below. So your first hope would be that if you simply integrate out the middle variables, the two sides would be equal. So you let the left-hand side be the integral of the Lagrange of the L function of before, so the exponential of the Lagrangian of the left-hand side of the Reidemeister move, and you let RHS be the integral of the right-hand side of the Reidemeister move relative to the middle variables. Only you hit enter and the computer, you ask the computer if left-hand side is equal to right-hand side, you hit enter and the computer says false. So that's bad news. So then you notice that in fact, if you look at the Lagrangian carefully, the x bottom variables, so the p bottom variables, may get also corrections, may get terms involving them from the terms below, from the features below. But the x bottom variables never get a contribution, only get contributions from the features above them. So you say, okay, let's integrate, Let's integrate and add also the x bottom variables to the mix. You hit enter, the computer says true. Now you're happy, but then you actually look at what the left-hand side is, and it says true because both sides are degenerate. Both sides were not actually computed. But then you say, so I want to integrate the relative to the lower p variables, but I'm not allowed because they appear, because they also appear in terms that I don't know yet, in features that I don't know yet. So instead, so what I want to show is that if I integrate with respect to the middle and bottom x variables, but look at the answer as a function of the lower p variables, then the two functions on the left and on the right are equal. That's what I want. So I'm going to do it by computing their Fourier transforms. Computing their Fourier transforms means that I add another triple of integration variables, pi, pj, pk. So basically I add a Fourier transform term, and I take the integral with respect to all the lower and middle variables, and now the computer prints true, and this time it's a reliable true, because when I ask it to print the left-hand side, it gives me a mess. But it's the same mess for both sides, so it's equal. I'm genuinely running out of time. Invariance under the other Reidemeister moves is proven in the same way. You must be asking, where is all of this nonsense coming from? I'm not answering now because I first want to tell you that there is more. So first of all, if you want to look modulo epsilon cubed instead of just modulo epsilon, here are the corrections you have to add to the Lagrangian. Second, there is a whole list of other types of invariants that are probably, that either certainly or probably have integral formulas. I won't go through it. And then maybe I'll only tell you that there is also an SL3 version. I didn't at all tell you how the first version was connected to SL2, but I'll tell you that there is an SL3 version. In the SL3 version, you have to use two formal variables, T1 and T2, and you let T3 be the product of T1 and T2, and you have 6 variables for each edge. Instead of 2 variables for each edge, you have 6. So P1i, P2i, P3i, X1i, X2i, and X3i. And then you, this is the Lagrangian. Hate it, hate me, it really doesn't matter. And here is a computation that proves that Reidemeister 3 holds for this Lagrangian. Here is a computation for the trefoil. This turns to be extremely slow. However, and the reason is that the integration program computes the Feynman diagrams each time afresh. If you kind of pre-compute the Feynman diagrams, well, that's what the Feynman diagrams end up looking for various features. And then you write a very quick program that just sums the Feynman diagrams. Then it becomes an efficient program. So let's compute theta of the node 3, 1. The answer is, first of all, the Alexander polynomial, and secondly, a polynomial in 2 variables. Polynomials in 2 variables are extremely difficult to read, it turns out, if you're humans. So here's a lovely thing that you can do. You can plot them in 2 dimensions. So basically what I do, here is a little program that plots the polynomials in 2 dimensions. And the way I do it is as follows. So powers of T1 goes this way. Powers of T2 goes that way, basically in the direction of some cubic root of unity. And therefore powers of T3, which is T1 times T2, go in this direction. And what I do is, if I see a monomial T1 squared, I put a hexagon at the position T corresponding to T1 squared, and I make the color of the hexagon blue if the coefficient is negative, and red if the coefficient is positive. And I let the shading be proportional to the magnitude, actually the log of the magnitude of the coefficient. So this is the invariant of the trefoil. This is the invariant of the Conway knot, shown here. This is the invariant of the Kinoshita-Terasaka knot, shown here. These two are notoriously different to tell apart, and theta clearly shows that they're different. And I'll show you a few more examples for fun. Here is the GST 48, a 48 crossing by Gompf, Sharman, and Thompson, which may be a counterexample to the slice ribbon conjecture, so it's interesting to compute things that have to do with it. Here it is as a list of crossing. Here is the invariant of it, and it computed in 11 seconds. Here it says 27 seconds because my computer was running hot when I did this computation. When my computer is cold, you know, when the computer runs hot, the CPU slows down. So when my computer is cold, it computes this answer in 11 seconds. This is a 2-variable polynomial. Here is the invariant of a certain random 250 crossing knot. Again, if you're used to other knot invariants, 250 crossing is beyond the imagine. It's way beyond what you can imagine. This is computed, and I have no idea what this means. So it looks a little bit like, what is it called? Diffraction patterns on a Like if you put sand on a hexagonal table and shake it, I have no idea why. And finally, here is theta of the Rolfson table of knots. So if you see patterns here, good, I see patterns too, but I have no idea what they mean. This all is very, very fresh, I should say. And I'm out of time. So I'm not going to tell you that there is prior art. This is probably equal to the two-law polynomial of Ortsuki, and it's closely related to work of Garofalidis and Kashaev, except they all got stuck at 11 crossings. Like they didn't have formulas that allow you to compute it to basically hundreds of crossings. I should tell you that theta sees topology. So it gets a genus bound, and therefore there is reasonable hope that it may be able to say something about the ribbon property, but again, I have no time to say anything about it. And now I'm 40 seconds over time, so I'm definitely not going to tell you where is it coming from. But it's coming from messy lit theory, and that's probably not the right way to look at it. And I don't know what the right way to look at it is. We don't know. So thanks again for inviting me to Beijing, and I hope I got you annoyed.
Thanks for the great talk, and please feel free to ask questions.
Am I right that you tried to do something like unknown coefficients for Reidemeister 3 in order to get integration over space of the same dimension, and after that, just a little bit like normalization for Reidemeister 1 and 2?
You're more or less right. So basically, I told you where it's coming from. So it's coming, well, I didn't tell you, but it's coming from fancy quantum algebra stuff. The fancy quantum algebra stuff is too hard to actually get the coefficients. It's just too complicated. At least our minds get blown. So instead, we figured out what form the answer should have, what form those Lagrangians should have, and then we searched in the space of these Lagrangians using undetermined coefficients, basically brute force. That's clearly the wrong way to do it. That's why there are better minds. This room is full of better minds who will find the right way to do it at some point.
Does it have to do anything with Vasiliev invariants?
Yes, it's probably the two-loop contribution to the Kontsevich integral, but it's not a useful way of thinking about it. It doesn't help you to compute.
Can you clarify the definition of the theta invariant?
Sorry?
Can you clarify the definition of the theta invariant?
Well, that was at the point of the talk in which I had like a minute left. So, if you give me another 20 minutes, maybe I will. Basically, the best definition is here is a program that computes it. So, where is the program? Sorry. Oh, here. So you, first of all, you define a number of functions. So the function R1, which really corresponds to a crossing with sine y and overside I and underside j, this function is given by this, the function the second function is given by that, and so on. And this is for the negative crossing. Basically, so I define a bunch of function, and then the program really tells you how to, what's the formula. Okay, you probably want a better answer than that. I'll give you one very, very quickly. So suppose you have a knot. I'm not bothering to indicate over and under crossings. But basically, you have crossings, each one has a sign, and then the invariant is a sum of three sums. Oh, first of all, sorry, even before that, you construct the kinetic energy matrix, which is essentially, well, there is a precise formula here, but it's basically the same matrix one of the matrices whose determinant is the Alexander polynomial. Except that instead of computing the determinant, you invert that matrix, and you let G nu alpha beta be this matrix inverse in coordinates alpha and beta, but this matrix has a parameter t in it, and you make the substitution, t goes to t sub nu, where nu is 1, 2, or 3. So really I get three matrices. And then I have a summation of three types of thing. One type is a contribution pair crossing, and this contribution pair crossing is given by this ugly expression here, so various combinations of these G nu ij's, okay? Then there is a double summation over pairs of crossings, and the contribution for a pair of crossings is given by these theta terms. And finally, there is a summation over rotations, so edges in which the tangent vector rotates, and it's relatively simple. It's given at the bottom here. Yeah, I'm sorry I can't give more than that. Well, the whole thing is about a month old. There will be a reference, hopefully, in not so long, but there isn't yet. However, people often say that, something is not proven until it's written, but here it's different, because here it's implemented, it runs, it passes all the tests. For example, I looked at all pairs of diagrams with up to 10 crossings that actually represent the same knot, and computed it for all such pairs, and if two diagrams represent the same knot, you get the same answer. So I mean, there is just no doubt that this works, this is right. It's not awaiting write-up because it's past implementation. It is awaiting write-up because, I have to feed my kids.
More questions? Thank you, Professor, for your speech. And I'm interested that could this method be generalized to any more semi-simple Lie algebras?
In theory, for every semi-simple Lie algebra, you get a power series in epsilon, so you get the epsilon to the 1 invariant, the epsilon squared invariant, the epsilon cubed invariant. In practice, it becomes harder and harder to compute, both to compute these formulas, and once the formulas are computed, so by the way, this was a nightmare to compute these formulas, okay? To figure out these formulas. But once they are computed, for higher Lie algebras and higher powers of epsilon, you stop gaining the computational advantage. You lose the computational advantage. So basically, here the Feynman diagrams end up being very simple diagrams. So the invariant is called theta because the Feynman diagram looks like the theta graph, the interesting Feynman diagram. Which really means a double summation over the features of the knot. For higher Lie algebras and higher powers of epsilon, you'll get triple summation, quadruple summations, and so on over crossings on the knot, and you stop losing, and you lose the computational advantage. So very likely theta, as written here, very likely theta is the best of this type of invariance. Hopefully it will have a better presentation at some point, but I doubt you can actually get a better invariant.
Okay, thank you, Professor. Okay. If no more questions, then let's thank Professor Bar-Natan again.
Thank you.